One was, yeah, yeah, one was this Fresnel diffraction, in which the source and the slit have finite distances between them. And the other one was this Fraunhofer diffraction. So in this one, we talked about that. So we talked that. Yeah, remember the Sunday extra class.
Sir, Sunday or Saturday?
Sunday, right? Because Arsenal had this exam on Saturday. Then we decided that it would on Sunday, and you have yeah, you come from your school at 2:30. So then we decided at 3 p.m. we will take that class, right? Yeah, is there any problem, Maya? Yes.
Yes, sir.
Yeah, we have problem. Okay. What?
No, sir, no, sir, I couldn't hear you, so I said yes, sir. So,
Oh, oh yeah. Okay then. Yeah, if we have some problem, then what? Then you can tell. Okay, because
no, sir, no
good.
problem.
Yeah, good. Then it's very good. Okay, so in Fraunhofer's diffraction, we talked uh, we talked that the separation between the source and the slit, that is infinity, right? So if you remember your refraction classes, if you remember your wavefront classes, if you remember your reflection classes, so how did we represented the incoming rays which are coming from very far away distance? How did we represent? Yes. How did we represent that situation? You guys have forgotten. So yes, hello Aisha, assalamu alaikum. Who got disconnected? Got dis- Mayam got disconnected. Yeah, so we represented the light rays coming from infinity as parallel lines, right? So the light rays coming from infinity are parallel lines, and the wavefront of the source which is at infinity, that wavefront is what kind of wavefront? Yes. You guys have gotten. So the wavefront is plane wavefront, right? When the source is at a very larger distance, then the wavefront is yeah. So when the source is at infinity, then wavefront is parallel, plane wavefront, right? So that is what I wanted to talk about. That if the source is at infinity, then the wavefront would be plane wave, right? So this we have discussed. That how many types of wavefront? One is the spherical, and then we have the cylindrical. But for the case of the very far away distance, the wavefront is parallel. These things we have. So for the Fraunhofer's case, diffraction, the separation between the source and this slit, this is infinity, and the wavefront would be plane wavefront. So these are the two cases for the Fraunhofer diffraction. Now let us talk about the observation or the experiment demonstrating this diffraction. This part is not in the syllabus, right? Fresnel diffraction is not in the syllabus, so this we will, right? Fraunhofer. So our source would be at infinity. That is the case. So the experiment to demonstrate this diffraction pattern is Young's, again this guy, but we have a single slit diffraction. Young's single slit diffraction or experiment. So what is this Young's single slit experiment? So uh, can we take in a lab can we take before we do that? So this is Fraunhofer uh, diffraction, right? So we will take a source from here and in a lab, right? In a lab, can we take a source to infinity? Can we do that experiment in the lab? Yeah. Let's say you have a room and you have made that room a lab. So can you take some bulb and the source, the slit, which are very far away distance with each other? Can you do that? You cannot, right? You cannot observe a Fraunhofer diffraction in the room because you can't have a source which is from very far away, right? Right. So let's say if this source is there, then these are the wavefronts that are coming, right, guys? Right. Yes, disconnected. Yeah. So we have this source, right? And these are the wavefronts. These are the spherical wavefronts that are falling on this surface, right? These are the spherical wavefronts. But is this Fraunhofer? This is in the lab. This experiment we are doing in the lab. So is this Fraunhofer diffraction? Yes, guys. Is this Fraunhofer's? Yeah, the source is there, the slit is there. So is this Fraunhofer's?
No.
Right, because this is finite. This is finite, so this is not Fraunhofer. So how do we make this source? We can do something and make this source as a source which is coming from infinity. And how we can do that? So let's say I have this source, right? And I have this convex lens. And if I put this source at the focus of this lens, right? If I put this source at the focus of this lens, then what will happen? Then it will go parallel, right? That is the idea of refraction, right? The rays coming from focus will pass parallelly to this principal axis, right? Right, guys.
Yes,
So
sir.
now, so now you guys can see that what kind of wavefront is this? What kind of wavefront is this? This is plane wavefront. So we have created a plane wavefront using this convex lens, and we have done this experiment in our lab, right? Because the Fraunhofer diffraction says that the source should
Which
be at infinity.
experiment, sir?
This Young's single slit experiment, right? This Young's single slit experiment, and we cannot take this source in a lab. In a lab, can we take a source to the infinity? We cannot, right? So then what we do is that we place a convex lens in front of this source such that this is the focus of this lens. then the wavefront that will come out of this thing would be plane wavefront. So that is what we'll do to make this young slit a Fraunhofer diffraction. So that is what we are doing. So what we are doing is we are taking this source, right? And then we are putting a convex lens, right, in such a way that, and this is our slit. So I have enlarged this slit, right? This is not the actual distance, but this is the enlarged one. So then this ray will come, right? And it will pass parallelly to this, right? So this is the slit difference A, right? And this is the lens, right? Convex lens, and this is the source, right? So I will not draw this thing, right? Okay, so now you guys see that this is how the rays are going. And we can
Assalamu
see
alaikum.
that walaikum assalam, you are late, half an hour late. So now
Yes,
you
yes,
guys,
sir.
yeah. So now you guys see that these are plane wavefront, right? And passing through this slit. So firstly, they are going parallel and again from here, right? The first, they will superimpose at some point. Let's say you have this screen, so they will superimpose in here, right? Like this. But you guys see that, right? These rays are going parallel. These rays are going parallel. So can you observe these rays on the screen? Can you observe these rays on the screen? They are not meeting at the screen, right? They are meeting at infinity. So they are meeting at infinity, so we cannot see them on the screen. So to put them on the screen, right? What will I do again? What will I do again, guys? Yes, what will I do again? I want to make these rays converge at screen. So I will put again a converging lens. Clear, guys? I will put again a converging lens in this position, right? So let me again draw the diagram because this will need some space. So let me again draw this diagram. So what did I do? I have this slit, right? I have this slit. I have this source, and I have put uh, this convex lens in front of this such that this is the focus. So this will go in this way, and then they will come parallelly, right? So this is the first thing, and then they will go parallelly from here, right? So they will go like this. What I want, what I want is that I want these rays to converge at some point. So I will again put a convex lens here, and then these rays will converge at this screen, right? So then they will converge at this screen, right? And this will also converge at. So this would be the central maxima, and this is the position of the fringe that we have done already, right? So this is the nth position of the fringe. So this is the separation between the fringe, right? So this is the nth fringe, and this yn is the distance between the central maxima and the fringe. So this is how we will calculate all the other things, and this angle we will call this as theta n, right? The angular distance of this nth fringe. So this is theta n. And what would be the path difference, right? So you see that this is the path of these two lights, right? So one is covering this distance, the other one is covering this distance, right? So this would be the path difference. So path difference would be how much? This would be the path difference, right? So I should have made the bigger diagram, right? Yeah, so I can. So this one, I made a perpendicular here, right? This is my slit width A, and this is my perpendicular. So these are the two rays. This is one, right? And this is the other one. So you guys can see that this is following this path, this is following this path. So path difference between these two is this much, right? Let's say this is x. So this would be the path difference, guys. Is this clear? So one is following this path, the other one is starting from here. So how much would be? This is the one path, path one, and this is the second path. From here to here, these are equal. So path difference is how much? This one, right? Clear? Is this clear, guys?
Yes, sir.
Okay. And we see that these are perpendicular. So this one, this is angle theta n. So this would be, these ones are perpendicular. So this would be 90 minus theta n, right? So this angle would be how much? This angle would be how much? Yes. How much would be that angle? Okay, let me make this diagram here. So you have this thing, right? This thing and this. So this one and this one perpendicular. This is theta n. So how much is this?
Theta n minus 90 or 90 minus theta n.
90 minus theta n. Absolutely right. Now you guys see that this one and this is perpendicular, right? This one and this one. So this is perpendicular. So how much would be this angle? Yes. How much would be that angle? Total is how much? Total is 90, right? Total is 90. This is 90 minus theta n. Let's say this is x we have used. So let's say this is z, right? So z plus 90 minus theta n is how much? How much is this plus this?
90.
90. So if you take this one in the other side, so this is 90 minus 90 plus theta n. So so how
Theta
much
n.
would be theta, right? That is what I am telling. So this angle, if I zoom this thing, let me name this as A, B, and C. So this Z is this angle, and this would be theta n, right? So this is theta n, and if I write that triangle in here, and what I have told that this is theta n, right? That is what we have found in here. This is how much? So you guys can see that this distance is A, right? So we have to find out this BC. This BC is the path difference that I'm talking about because the rays are going like this. So this distance equal. So only this extra distance, the second one is covering. Second ray is covering this extra distance. So that would be the path difference, right? So I have to calculate the path difference, and this is hypotenuse A. This is theta n. So this is the base, right? So what relates base, hypotenuse, and this thing? What relates that? Oh, this is not the base, right? So if I choose this angle, if I choose this angle, then what is this? This is the base, right? So this is perpendicular,
Perpendicular.
right? Because if I'm choosing this angle, then this would be the base. If I'm choosing this angle, then this would be the base. So I'm
Yes, sir.
choosing this angle. So this is base, this is perpendicular. What relates perpendicular and hypotenuse?
Sine.
Sine theta, right? So sine theta n, that would be how much? Perpendicular, which is BC by A. So BC would be how much? That would be A sine theta, right? So this is what we call the path difference. So path difference is how much? Which is x, which is A sine theta. Okay, so this is one thing. And if theta is very small, right? Then I can write sine theta as theta. So this is theta n, right? So sine theta n as theta n. So this x would be how much? That would be a theta n, right? This is my first case. Similarly, if you guys look at this triangle, let me name this triangle as, let's say this is M point, this is N, this is O, right? So we have MON triangle, right? So in triangle MNO, what is MNO? So this one is MN, this is YN, this is M, this is O, this is N. And what do we know? This angle. This angle is theta n, and the separation between the screen and the this slit is d, capital D. That is what we write, right? So this separation is. So now you guys tell me what relates. This is because if this is the angle, right? If this is the angle, then this is perpendicular, right? This is perpendicular,
Yes,
and this is base, right? So what relates perpendicular and base? What relates perpendicular and base? Tan theta, right? So tan theta is perpendicular by base. So if I write this thing in here, so tan theta n, that would be how much? That would be yn by d. So we can write yn as d tan theta n. And similarly, if theta n is very small, then we can write tan theta n as theta n. So then we can write this yn as d theta n. And we have already we have already found the value of theta n. So if we put the value of theta n in here, right? If you put the value of theta n in here, so yn would be how much? That would be dx by a. So for small angle, this is your separation, right? So this is your separation of nth fringe from central maximum, right? So this is all about diffraction. And then as we
Sir,
have, yes,
so your voice is really low.
yeah, so guys are telling me about that again, right? Why this is happening? Is this okay now? Yes, can you, is this okay?
Yeah, I can hear you, but it's like really low.
Why this is happening? So why does this happen? One, oh, this is very low. Oh, that is why. One minute. Okay, how is it now, guys? How is it?
Sir, it's clear.
It's clear now. Yes, Mariam, is it
Yes, sir, I can hear you.
Mariam, what about you? Is it clear now?
Sure,
Yes,
sir.
same. Oh, is
Yes,
it?
sir.
Okay, so for you it is not clear. For Arsalan it is clear. What is happening? Aisha and Mir, what about you guys? Can you guys hear me properly?
Sir, it's clear.
Oh, it's clear. Oh, my yeah, so my ears are gone, I guess, because I can't hear you guys properly. Okay, so did you guys understand this part? This would be the separation of an F fringe, and this is the path difference. And as we have done for the case of interference, for the case of interference, what did we find out? We found out the bright fringe and the dark fringe. So similar case will happen in here, right? Similar case will happen. But yeah, you guys please note down this part, right? So you guys, this part you guys have already noted, right? So you guys please note down this. And if you guys have any question, please tell me. Please tell me if you guys have any question. So this diagram is very, very, very important. If we understand this diagram, then everything would be clear. So how do we make this diagram? We make it, okay, I don't have any space in here. Let me just draw it. So we have this source, and then we have this lens, right? And the light rays are coming from here, right? They are parallel. So then first we make this one, right? And then this one goes parallel. and then we have this lens. So on the screen, they will merge it, right? And this will merge in here. So in here, we will get central maxima, and then this will decrease, and then we will get nth fringe in here, right? So nth, and this is theta and theta. So this is how we simply draw this diagram. Okay, so this is how we can quickly draw this diagram. But this diagram is the full, right? And the path difference would be, this is this separation is A, this is the perpendicular, and this is the path difference, because this one is following this path, this one is following this path, and this path is extra path, right? So that path is called path difference. Okay, whenever you guys want me to scroll down, please. Yeah, this one I forgot. So this is right. This is a slit. This is a screen.
Yes, so you can scroll down.
Okay, so then yeah, whenever you guys have noted it down, please.
Yes, sir, scroll down. Yeah, whenever you guys have completed putting it down, please. Yes, sir, done.
Yeah. Okay, so now let us understand, and we will not derive because yeah, derivation is not there for this one. So we will directly write. Right, we will directly write the position of the secondary minima and secondary maxima. Right. The first one that we will talk about is the separation of the nth secondary minima. Right. So for secondary minima, for secondary minima, the path difference is n lambda. Right. So and where n goes from, n is 1, 2, 3, and so on. So this is the path difference. And from this one we can calculate the separation of first secondary minimum, right? So, but before that, let us find out the nth fringe separation. So nth fringe separation would be how much? Yn is xd by a, right? Yn is xd by a, so this would be how much? This would be n lambda d by a. So this is the nth fringe separation. So if we calculate first secondary minima, so first secondary minima, that would be how much? That would be y1, right? So that would be lambda d by a. Okay, and then secondary minima, that would be how much? That would be y2, which is lambda 2d by a. So that is the second, and we can also calculate the third one. So third one would be 3 lambda d by a, and so on. So this is the position of the first and second, all these secondary minimums. And then we can also calculate so we can also calculate the separation of nth secondary max. And that would be how much for this one? For secondary maxima, we have path difference, that is 2n plus 1 by 2 divided by this is the path difference. And you guys can ask that why we don't have 2n minus 1 by 2. Here this n goes from 1 to 3 and so on. But in interference, we saw that this was the case, right? Because you have the central maxima, you have this central maxima in such a way that this engulfs all the other this part, this maxima, this bright fringe or this central one engulfs all those regions, right? So this one is the bigger one, and then subsequent one is the smaller one, right? So this one, and then this is how it decays, right? So this one is the bigger one, and it engulfs this 2n minus 1 by 2 part, right? So that is why we don't have this 2n minus 1, because this 2n minus 1 by 2 is already there in the central one. But we didn't see this case in the case of interference, because in interference, all these were similar, right? all these were similar. This separation was also similar. So that is why we don't have this 2n minus 1 by 2 part, right? Okay, so we'll talk about this central one in a moment, but let us understand the separation. Nth, so separation of nth fringe of secondary maximum, and that would be how much? Yn is xd by a. So this is x is 2n plus 1 by 2 lambda d by a, right? This is the nth separation. And if we calculate the first secondary maxima, that would be how much? Here n goes from 1 to 3, right? So y1 would be 2, 1 plus 1 by 2 lambda d by a. So this is how much? This is 3 lambda d by 2a. This is y1. And then you have a secondary maxima. That is how much? That is y2, which is into 2 plus 1 by 2 lambda d by a. So this is 5 lambda d by 2a. This is the second one. And if we calculate the third one, so that would be how much? 2 into 3, 6 plus 1, 7 by 2 lambda d by. So that is the position of all those secondary maxima and secondary minima, right? So that we can calculate. And you guys can also tell me, right? So the next topic is width of the central maximum, right? So we have to find out the width of the central maximum. And we know that what is the central maxima. So this is the slit, right? And the rays are coming and they are converging at this point. This is the central maxima, right? And then we have this point is what? This a point and this point is the first secondary minima. This is also the first secondary minima, right? This is the central one. This is the central maxima. And after that, there would be first secondary minima, right, guys? So width would be this thing. That would be the width, guys, right? Right, guys. And we know that this angle would be how much? So this angle is how much? That is theta 1, right? So theta 1 is the angular width of the first secondary minima. That is the theta 1, right, guys? Right?
Yes.
So theta 1 would be how much? We know that theta 1 is the angular position or angular width of or angular position of first secondary minimum, right? And we know that this is how much. So this is theta is how much? That is x by a, right? Theta is x by a. So we know that theta n is x by a, and for minima x is n lambda by a. So theta 1 would be how much? That would be lambda by a. So this is the theta 1, right? And if we want to calculate the angular width of this maxima, right? This is the angular width of the central maxima. So angular width would be how much, guys? What would be the angular width?
Sir, Q1.
Theta 1 plus theta 1. That is the total angular width.
Yes, sir.
So angular width of central maxima, that would be how much? That would be 2 theta 1, which is 2 lambda by a. So this is, let's say this is theta, which is 2 lambda by a. This is maximum, right? This is angular width. Now what would be the linear width? Linear width would be y1 plus y1, right, guys?
Yes, sir.
So linear width would be how much? Linear width of central maxima. That is y1 to y, right? And we know that how much is y1. Y1 we have calculated, and that is lambda d by a, right? So 2 lambda d by a, right? This is so y1 is lambda d by a, so 2y1 is 2 lambda d by a. So the y max, right? Or let me call it as y. So width, let's say y. This would be 2 lambda d by a. So this is the width of the central maxima of the diffraction. Do you guys remember what was the width of the central maxima of the interference? Do you guys remember that? Yeah, you guys please check that, and yeah, because one question is dependent upon that thing. So we'll do that part in here, but before we do that, please note it down. And if you guys have any confusion, any question, please ask me. So if you guys have any confusion, please ask me. Otherwise, please. And whenever you guys want me to scroll down, please tell me.
Yes, sir. Done.
Done. Then please click down. This is not the right. We have this. Yeah, then we'll do one question and then you guys will understand this. Whenever you guys want me to scroll down, please tell me.
Yes, sir. Done.
And remember, we are doing all these calculations for small angles, right? Because if we have a larger angle, then we have to use this thing, right? So path difference would be a sine theta. So that we will use. But for our case, the angles are small. So this part you guys have. Then please note down. This part you have also noted, right, guys? Then please yeah, whenever you guys have noted it down, please yes, noted, guys.
Yes, sir.
Let us do one question and then it will be very easy to understand. The question is the question. So in a single slit experiment, right? A light of wavelength 600 angstrom. How much is angstrom? Yes, slit width is 2 millimeter, right? Separation of slit from screen. So separation of slit from screen, that is 2 meters, right? Then find separation of first secondary minima from central maxima, and we have to find both angular and linear, right? So these are the two things that we have to find. And the second question is separation of second secondary maximum, right? And again angular and linear linear separation. So these this is the question. Now you guys already know, right? So what are the things which are given? This is lambda, right? So what are the things which are given? Let me- So given is lambda, which is 600 angstrom, which is how much is angstrom, guys? Slit width A is given 2 millimeters, and the distance separation of slit from screen, that is capital T. This is 2 meters. So angstrom is how much? Everyone, any answer? So 10 to the power minus 10 meters. 10 to the power minus 10 is angstrom. Okay, 2 millimeter is 2 into 10 to the power minus 3 meters. And this is in SI units. So all the things are in SI units. And we have to find out, first we have to find out the separation of secondary minima from central maxima. And both the things we have to find out. So we have to find out theta 1 and we have to find y1 of minima. Right, so this is we have to find out. What do we know? We know that theta n is x by a, and for the minima one, this is n lambda, right? So n lambda by a is the separation of the nth one, and yn is how much? That is n lambda d by a. This is the linear one. So this is linear separation, and this is the angular separation, right? So we have to find out the first minima, first secondary minimum. So we have to find out theta 1, which would be lambda by a simply. And we also have to find out y1, which is lambda d by a. So lambda is 600 into 10 to the power minus 10. And how much is this thing? A is 2 into 10 to the power minus 10. So this is 300 and then this 3 goes in the numerator. So this is 3 into 10 to the power 2, 10 to the power minus 10, 10 to the power minus 3, right? This would become how much? So this is 5 minus 10. This is 3 into 10 to the power minus 5. So this is the angular separation, right? This is the angular separation. And what would be the linear separation? So linear separation is lambda is 600, d is 2, and this is 10 to the power minus 10, right? 600. And then this is 2 into 10 to the power minus 3. So again 300, and this is 600 into 10 to the power minus 10 and 10 to the power 3. So this is 6 into 10 to the power minus 5 meters. That would be, and this is in radian, right? So these are the two values. Is this clear? Now you guys calculate for the secondary maxima one. You guys calculate the secondary maxima one and tell me what you guys do. So we have 46 is already there. Yeah, so let me do that. So we have to find out theta 2 and y2, right? For the maxima one. So what do we know? We know that theta n is n plus 1 by 2 lambda by a for maxima, and yn is 2n plus 1 by 2 lambda d by a. So these are for maxima. And we have to find out theta 2, which is 2 into 2, 4 plus 1, 5 by 2 lambda by a, and y2 is 5 by 2 lambda d by a. So 5 by 2 lambda is 600 nanometers angstrom, and then this is 2 into 10 to the power minus 3. So this is Teresa, right? And then this is 1 and 150. So 15 into 5, that is 75 into 10 to the power 0, right? 1 and 10 to the power minus 10 and 10 to the power 3. So this would be 3 plus 1, 4. So 7.5 into 10 to the power minus 5 radian. Similarly, this would be how much? This is 5 by 2, 600 angstrom meters, 2 millimeters. So this will cancel out. This will. So this is how much? 15 and 0, 0 into 10 to the power minus 10, 10 to the power 3. So this is 1.5 into 10 to the power minus 4 meters. So you guys can see that the position of secondary maxima is very far away, right? That is very far away. So this is minus 5 order, this is minus 4 order. So one order above, right? That is what we expected. So is this thing clear, guys? Is this question clear?
Yes, sir.
Okay, then please note it down, and if you guys have any doubt in the question, please ask. So please note it down, and I will give one question as you. Okay. Yeah, whenever you guys have noted, please tell.
Yes, sir. Just a few more minutes.
Yeah, and in the meantime, I can tell. Yeah, whenever you guys want me to speak. And
Yes, sir. Done.
this one is the last topic. So one very important question. We'll do a couple of question rounds. Question will do and then this chapter is. But I guess we have. So please on Sunday you guys please come and we'll start the chapter.
Yes, sir. Done.
Done. Okay, so yes, everyone noted. So now we have another question, and this question you guys will go. And this is another easy question. Question is this question. A parallel of light uh, of 600 nanometer. So how much is nanometer? Falls on a narrow slit. Yeah, what is nanometer, guys? Please tell me. And resulting diffraction.
Sir, nanometer is like it's like a very small unit of measurement, sir. I think
Yeah.
so it's like 1 billionth of a meter or something.
So what 1 meter of what? Yes.
No, sir, like 1 nanometer is like 1 billionth of like a meter, like 10 raised to 9, right?
Yeah. So 10 to our minus. If we are calling small, so that would be minus. Yeah.
Yes, sir. Like it's like one by
Yes,
one.
absolutely correct. So 1 nanometer is 10 to the power minus 9. So is observed on screen 1.2 meter. So then you have to find out it is observed that first minima, right? And this is secondary minimum, right? So first minimum is at a distance of 3 millimeter from center of so calculate the slit calculate the slit width, right? So you have to calculate, let's say, the parallel lines light are coming, and then this is the slit width, which is A, and this separation is given, which is 1.2 meter, and this is the central point, and this distance is given. This is 3 millimeter. This is the first secondary minimum. And this thing is the uh, central what maximum. E is also given. You have to find out what is A. This is the question. You please note it down. And yeah, you guys do this question at your home. And in the next class, please tell me the answer of this question. Okay.
Okay, sir.
Please note down this question and then we'll do another question. That one has been asked many times, and that question is yeah, whenever you guys have noted it down.
Yes, sir. I'm done.
Done. Okay, so the next question is how many number of fringes can a Young's double slit experiment can accommodate in a in a single central maxima of Young's double slit, not double slit, but single slit, Young's single slit experiment. Right. So question is, what is the question? That you have a maxima of central single slit experiment, right? So you have a central maxima of Young's single slit experiment, and in this single slit experiment, how many how many number of fringes of the double slit experiment? Because we know that for double slit experiment, this is intensity is similar, right? The intensity is similar for Young's double slit experiment. For the single slit experiment, the intensity, when we will do the intensity curve, so you guys will see that the intensity goes right. The intensity goes like for single slit. But for the double slit, the intensity goes like so all the intensities are equal, right? So this is a double slit, and this is a single slit, Young single slit experiment. So this is the question, and how we can calculate that? So we can write that this is how much? This width, this width is how much, guys? How much is this width? This is the width of the central maximum, right? And we have calculated that y of a single slit, right? Single slit experiment. That would be, these are from here to here. This is the width of this double slit experiment, right? So let's say this is ym, this is ym, all these are equal, right? So this would be 1, 2, 3, 4, 5. Let's say n number of have double slit fringes, right? Is this thing clear? Is this thing clear, guys?
Yes, sir.
So we know that for single slit, this is central width is 2 lambda d by a, right? Am I right? This is what we have just calculated now. And for double slit, this is simply lambda d by d, right? So this t will cancel, this t will cancel, and we will get n as 2t by a. So this would be the number of fringes that we will obtain. So we'll write the numbers in the later class, and yeah, then we can see, we can check what would be the value. So if you have the slit difference of single slit, slit difference of the double slit, then you guys can calculate number of fringes. So you guys please note it down, and then we'll stop it. And if you guys have any question from this part, then you guys can ask. Okay. Yes, please note it down. Yes, whenever you guys have completed